saw you, so maybe you can turn on the mic and share your screen. So again, we have a little bit less than 20 minutes, so we can have a few questions from the audience. Please, you're welcome. There it is. We start to see something coming. Okay.
All right. Can you see my presentation? Okay.
Yes, not in presentation mode, but we do see it. And now it is in presentation mode.
Okay.
Very good.
Perfect. So continuing a bit on the line that Yanis just started, I initially thought I was going to talk about seismic loading of monopiles. Because I'm both a structural engineer and a geotechnical engineer, I work on both the structures and the monopile. So I thought I was gonna give a taster overview of the activities that I've been involved with. So as Yanis was saying, we're now concerned with building offshore wind farms in seismic zones. So if you look at the map of the world, this is where most of our wind farms have been built up to 2015. And since 2018 mostly, there has been a lot of project ongoing in Taiwan, in Japan, in China, and this is only going to grow. And what happens in those zones is that you have layers of liquefiable soil at the top layer, which could be problematic and are not typically addressed in design guidelines. So how you address the case of liquefaction in foundation design, and how do you address the case of earthquake loads in structural design of both a non-trivial problem that the industry is currently facing. So now if you look at the right-hand side diagram, you have a typical schematic of an offshore wind turbines. And if you're a civil engineer, what you're going to be most concerned about is a foundation, which is typically a monopile for 80% of the foundations. It is a monopile at the moment. And then a transition piece, and then a tower that's supporting the turbine. And I'm going to look at each of those elements in the coming few slides. And we're interested both during earthquake, but also post-earthquake, because it's all well and good that it survives the earthquake, but you also want to know what is the remaining capacity following the earthquake. So now I'm going to have a look at a very typical diagram in offshore wind, on which I have added recent concerns on earthquake. So in this diagram, what I have is a normalized power spectral density of a range of frequency that are pertinent for offshore wind. The 1P range of frequency is the rotor frequency. The 3P is a rotor blade frequency. And then in blue, I have the wind frequency, in dark blue, I have the wave frequency. Add on top of it the range of frequency of your earthquakes. So here I've picked two. I've picked Kobe and Chi-Chi because they're both relevant to East Asia, and they're quite different type of earthquake. Kobe is a large frequency component earthquake, and Chi-Chi is a much lower magnitude earthquake that has a lot of components in lower frequency that are going to come and excite this orange line that I've put there, which is a natural frequency of your wind turbine structure. And the one in dashed line is the second mode of the turbine, and there is a debate as to whether this mode is going to be excited and whether we need to worry about it. So that kind of planted the scene as to one of the concern we have, which is the design that we're doing sufficiently robust in terms of frequency, and how can we adjust the soil frequency so that it's not too bad. So in this talk, I'm going to cover results that are published in 3 papers very, very recently, actually. The bottom 2 are concerned with the monopile. The last one actually got published 2 days ago, so I haven't had the time to incorporate the results in this talk, but you can go ahead and some of it is used from that. And the top one is on the superstructure and the transition piece, and in here, I really want to acknowledge my co-authors, in particular the 2 students who have done the work, Chris Hamilton for the 3DFE work, and Jun Tae-seong, who did all the centrifuge tests for the monopile, as well as my collaborators in the Schofield Center, who I don't think need any introduction. Right, so I'm going to start with the monopile. And for the monopile, it's very difficult to do numerical model, as was highlighted by the past question, because there is presently no experimental data to validate those models. So we started small, and we started by doing some centrifuge tests on actually small diameter monopile, because it is extremely challenging to do large diameter, and the low-hanging fruit was to do some small diameter monopile tests. And this was done in the Turner beam centrifuge at Cambridge. I think a lot of you would know the centrifuge. And in this centrifuge, we can apply earthquake loads using a servo hydraulic earthquake actuator and a container which replicate the correct boundary condition using an equivalent shear beam model container. And with this setup, we can apply literally any sorts of earthquake that we want to apply, be it Kobe or Chi-Chi. Here I have Imperial Valley, but also sinusoidal waved targeted frequency. So looking at our test setup, what we chose to model is a layer of dense sand with a layer of liquefiable sand on top of it, in such a way that 50% of the monopile was embedded in the dense sand. We chose an Abadie ratio that was relevant to offshore wind with a small diameter, and the reason why we chose that will become apparent in the test setup in the next slide. And we applied a horizontal load at an eccentricity that will mimic the monotonic load that's applied on top of a wind turbine, but not concurrent to the earthquake. We used a lump mass to replicate the upper structure mass on top of the structure and its inertia, and then a set of strain gauges, VDTs and piezo, to get some information about the response of our system. And because we wanted to study the response before and after the earthquake, what we did is that we used 2 piles. And that's the reason why we had to go small diameter while respecting the geometry, because we wanted to have 2 piles in our container while respecting sufficient distance to not have boundary effects. So we have our 2 pile, and the first one is pushed before the earthquake to get the monotonic response. And then the second one is pushed, but after the earthquake to get the monotonic response post-earthquake. And that's a setup there. That's a photo of the test before it was loaded. And the one thing that I should say here is that the results that I'm going to show in the following are the results of the first test, which was dry, so no liquefaction. But in the paper that just got published, you can find the following tests, which was saturated. I'm still going to start with the dry one. Let's zoom on the setup at the top. It was important to do the dry one at the beginning to validate the test setup, because we had never done a earthquake push at height in the centrifuge before. And that's the type of results that we got. So in here, we're doing just a simple sine sweep to find the natural frequency of the structure. And you've got this big blue line in here that is the response on the top, so the response from those MEMS in here. That gives you the natural frequency of your structure. Now, if you rig your eyes to this blue line, this is the same sine sweep after the earthquake, where you can see that the blue line has not moved, it has simply increased. So that means that the natural frequency has not shifted because of the series of earthquakes that we've applied in the middle. So that was an interesting result. And this is the response that we got for one of the earthquakes that we had in the middle. What did I choose? I chose 15 cycles at the natural frequency. Here, 10 cycles, sorry. 10 cycles at the natural frequency. And you can see here by comparing the orange line to the blue line that we get an amplification factor of 5.2, which is quite large. So that gives you a taster of the sort of results that we get in this sort of study. Of course, there's a lot more to look at once you get saturated soil, and that's all shown in the paper. Now, a quick note on the pre and post-earthquake response, which was probably what I was the most curious about, having worked on the PISA project just before. Does that change our method for monotonic loading or not? And in here, we're in dry soil. Of course, further validation is needed for both saturated soil and larger diameter pile. But what you can see on this diagram is in gray, the pre-earthquake response, and in black dashed line, the post-earthquake response. And actually, from an experimental point of view, it's very similar. So in this particular test for this particular geometry, and bearing in mind that this is dry, then the response is pretty similar. And if you want to know more about the saturated test, I will leave you to scan this QR code and have a look at the paper. Right, so just before I finish, I'd like to give you a taster of what I've been doing on the structural aspect of things. It is very, very difficult and consuming computationally to model perfectly both the foundation and the structure. Just modeling the structure takes us 3 weeks on a supercomputer at Arab to run the simulations. So imagine adding sandy sand and the whole body of soil, that becomes extremely complicated. So what we decided to do in this project is to model the mast and the transition piece accurately, and then to go with a very dummy, simple model for the soil with just springs, but springs that represent the hysteresis. And we don't have anything on liquefaction here just because at the time we hadn't done any tests on the centrifuge to give us an idea of how that could be captured properly. So let's start with that. And this is a sort of details thing that we're trying to model for the transition piece. There are 4 types of transition piece currently on the market that are used, but the gratis connection holds really good chances to being used in seismic areas. So we started our analysis with this. And it's basically, you've got the monopile coming here, the superstructure coming here, and the whole thing is bonded using grout and shear keys to maintain the stability. And that's a photograph of our 3D FE model. With a zoom on the shear key region. And first, looking at the mast response, what we looked at is the displacement at the top, because if you're a manufacturer, that's sort of what you're interested in. It guarantees the integrity of your blades. So it's quite important to look at that. At the bottom, you've got the acceleration that we provided to the system. And at the top, you have the hub displacement. And we've tested 3 types of soil condition. The first one is a clamped one, which is typically used by the structural engineer. It's kind of a tap in the back to say, please don't use that. And then we tested a soft soil and a stiff soil that we borrowed directly from the PISA project. And in here, what you can see is that you get a shift in your displacement, but also a damping of the displacement that's quite dramatic depending on the type of soil that you're using. It was to be expected, but it was mostly to show that this is important to include. With regards to the natural frequency, the first mode doesn't change that much. It changes by 7%. You can't see on this diagram, but I can tell you. The second mode changes a bit, and we've done further analysis to see how important that is for the response of the whole structure. Now, looking at the transition piece, what is important is to guarantee the integrity of the transition piece throughout the earthquake and at the end of the earthquake. So we looked mostly at cracking rather than stress concentration. And in here, what you can see is a pre-seismic response where you have almost no crack, where we're just applying the operational load, and this is what we get. But this post-seismic response starts showing some quite large damage. At the shear key, you have circumferential cracking along the shear key, and at the top of the transition piece, you have some deterioration of the top connection. Now, that might be a problem and that might not be a problem, depending on where it is located. But if you've got too much cracking towards some region of the transition piece, you can have some ingress of water over time that leads to corrosion and deterioration of the transition piece until it's no longer usable. So that's the sort of question that we were trying to answer with this paper. It just got accepted for publication. So for those of you who are interested, I can send you a PDF copy of it. In conclusions, large diameter monopiles response to cyclic loads is an important research area for offshore wind at the moment. I'm sure a lot of groups are starting to work on this if they haven't started already in the past few years, with a better understanding of liquefaction effects on the monopile response being really at the top of the list. In the test that I've presented today, I've seen no change in natural frequency post-earthquake, but this needs to be validated further for bigger geometries and, most importantly, for saturated soil. Pile response to ground motions close to the first bending mode of resonance display large amplification, but quite reassuringly, the monopile response to monotonic load was quite similar post and pre-earthquake. In this test, again, that needs to be extended to larger geometry and saturated soil. There is a necessity of modeling the soil in structural analysis, and we've been having this conversation with structural engineer a lot. This is usually discarded or clamped or an elastic spring with no hysteresis, and that practice needs to change, and that starts by having a better collaboration between structural and geotechnical engineer. The response to the transition piece to earthquake is also important to infer which technology we're going to prefer towards in seismic zone, be it grouted or bolted. Both of them have major problems. Until transition piece less technology are ready, which is currently being investigated. Those results need to be extended. For the monopile aspect, I've repeated it quite a lot over this presentation, but saturated soils and large diameter piles are needed. And also, for those of you who have a keen eye, you would have seen that the frequency of our structure was not quite the one that would be at full scale. So those tests that we have done in the past year address those problems. From the numerical aspect, soil liquefaction will need to be integrated in a simple manner, because otherwise computational time completely explode, and other types of connections have been also studied in this analysis. Right, okay, that's it for my presentation. I unfortunately can't stay to the event for too long because I have a teaching commitment later. But if you have any questions, please feel free to send me an email. I'll be very happy to answer. Thank you.
Thank you very much, Christelle. We have half a minute for if you want, for a short discussion. Anyone in the audience working on monopiles? Yes, please. It's your turn, man. Question is coming, Christelle. Just a problem with the microphone.
Hi, Christelle, this is we have been working on similar things. So on the numerical side, just to say that we have been doing analysis with modeling saturated soil and liquefaction, and it does actually show that one of your points were that, for dry soil doesn't show change on the frequency of the system. Well, for liquefaction, it can change quite dramatically the overall response and can bring it to, under certain conditions, to the frequency range that is important and leads to amplification. But as you said, it's very expensive computationally.
Yeah, so I can't imagine building your type of model to my type of model for the superstructure, because we're going to need.
So we've done the whole thing with the structure and the soil, but it
the
took months.
transition piece, adding the detailed transition piece, that becomes because you need to model grout. So it's another complex quantitative model and takes forever. No, for the structure we had simple quantitative model, but still with the complexity of the quantitative modeling for the soil, it does take, it's very expensive. I believe that.
10 seconds.
It's over. Christelle, thank you for a very nice presentation. The transition piece, is it cracking because it is bending?
Yeah, so the 4-point bending mode is the first mode of breaking the transition piece as a whole, but it's actually shearing inside the grout that causes the cracking. So you need to get the detailed quantitative model that can enable that shearing properly. And
how do you model it?
We use a Winfried's model for grout.
Okay. I'm wondering whether it is possible to design, let's say, the transition piece to apply some kind of capacity design.
Sorry, I didn't hear that.
Would it be possible to apply some kind of...
Okay, try again.
Is it possible maybe to apply some kind of capacity design so that instead of having failure at the transition piece, it's kind of over-designed to have failure somewhere else, or maybe inside the soil?
Yeah.
Or is it good that you have nonlinearity in the transition piece?
I think it's good to have nonlinearity because it dampens some of the vibration. So it has some advantages, but I wouldn't be able to answer that question from a designer point of view, to be honest.
Okay, thank you.
So thank you again, Christelle, for participating to the workshop, and have a nice lecture. And now here we move forward. Hauke Zackert from Darmstadt Technical University. So the floor is yours.
Yes, thank you. Welcome to my presentation. I'm Hauke Zackert from Technical University Darmstadt, like Marco said. Microphone. Okay, so now we start again.